Hello maths fans, I am back with Grant from 3 Blue 1 Brown, and Grant has asked me to teach him some fluids.
Yes, I have.
Which I am super excited about. Like, this is like my dream. So not only did I get to teach Brady some fluids, now I get to teach Grant some fluids. I've decided what we're going to do today is something called potential flow
Okay.
and the method of images.
Okay.
So potential flow in fluids, it's like a very idealized setup. So you have it's an irrotational, an incompressible, and an inviscid fluid. We don't need to worry about what those words mean. It's just certain labels of it's quite an ideal situation. So the sort of setup is to think about sort of flow fields. That's the idea here. So we're thinking about the sort of standard fluid flows that can occur. So we're going to be in the XY plane, so 2D. And then I'd say we have some fluid moving at, let's say, an angle alpha with the positive x-axis. So sort of if you were to try and draw that flow field.
And infinite, there's no boundaries.
There's no boundaries, just the whole thing, and it's all moving in the same.
So it's all moving at the same angle.
And the same speed, yes.
With respect to the x-axis.
Perfect. Okay. Exactly, something like that. So it's sort of this is what we call a uniform flow, and that there is going to be alpha, our angle. Okay, so that's like the simplest setup. Then we have some other type of flow which we call a stagnation point flow, and so this is where you have a point where at this point there is zero flow, but there's kind of flow around it.
Okay.
So this won't necessarily be a uniform flow, but like there's something happening, but there's this sort of central point where there isn't any flow.
Okay.
As an example, if we take this to be the origin, and then you sort of think, well, if I were to have sort of some flow coming in like this, and then like this, but at the center, it kind of, there isn't any flow.
Well, then I guess, yeah, there's sort of something where there's flow lines.
Yes.
Doing this sort of thing. And like the vectors along that get more and more looking like that as you get closer.
Yes.
So I think if something happened to be precisely on the y-axis, then it just approaches the origin and never quite reaches it.
Yeah, because it goes so slow.
Anything that's epsilon away from it generally gets shifted into the positive x direction.
Yeah.
Okay.
Yeah, that's the way to think about it. So we have this stagnation point flow, and then the other one that we might be interested in would be a source or sink. So we're going to consider a source. We're going to call it a line source. And again, this is going to be at the origin, where it's just sort of throwing everything out equally in all directions.
All right, so just when you say line source, though, there's just a single point that is the source?
Yes.
And the sense in which we're talking line is that it's lines going away from it?
Exactly.
Okay, sure.
So it's just equally shooting everything out in all directions.
And I'm doing what you want me to do, which is to draw what I think you're describing.
Yes, absolutely. This is just, hopefully, this one's a little bit trickier, the stagnation point flow. But these are like sort of the canonical fluid examples that we consider in the setting. And what we want to try and do is construct a mathematical equation or formulation for each of these, and then think about how we can use that to then build more and more complicated particular fluid flows.
Sounds good.
That's the kind of idea. So then what we're going to do now is consider the uniform flow from earlier and a source.
Okay.
So now what I want is out here, some flow coming in at some constant speed.
Gotcha.
Then you've got a source here, which is shooting out in all directions equally. And I want you to attempt to draw what the streamlines or the velocity field might look like. Using your complete sort of physical intuition.
My thought is that they'll add together linearly. So if in the original, what do you call it, line source flow, if we would have had some vector that goes out kind of like this, then we'll be adding it to whatever the uniform vector is, right? And so instead we'd have something like that. So as we are farther away from this, it generally will look positive.
Yeah.
But as we get closer to it, it seems to be pointed more out. More out, that kind of thing. And similarly here, instead of pointing backwards, we're going to be adding that. So something that maybe making it messy by putting all the additions in there. But something that's kind of that general form. So like as we're closer to the center,
So even here, so it's kind of shooting out, but then sort of very quickly coming back on itself, isn't it? Almost like I want to say like a pitchfork, but maybe not. Maybe I'm just picturing pitchforks wrong. I don't know. But okay, so it's a bit trickier.
Like long
but
flowing hair. Sort of like comes up from the top
yeah,
of the
nice.
head
Yeah,
and
that's
goes
back.
down
Yeah,
both
okay.
sides.
Long flowing hair. Okay. So the way we sort of try and turn these lovely diagrams into maths is using something called potentials, which is why it's called potential flow. So for the uniform flow, we have our potential W is written as constant U, which is the uniform speed that we're moving at, e to the minus I alpha, and then Z. And so this describes our uniform flow with angle alpha, where we are moving at constant speed u. The alpha is appearing in the e, so that's giving us the cos and the sine, so like the components of the vector. And what we can say about w is we get the velocity components from our potential theory by differentiating dw by dz.
Okay, and so this is a complex value.
This is indeed complex, and this is equal to little u minus iv, where u is your x velocity component and v is your y velocity component. So this has just come from the picture. And then given this formula, if you then calculate dw by dz, u e to the minus I alpha, so that's u cos of alpha.
Oh, I'm sorry. Okay, so this is all, because that's just a constant.
Minus I sine alpha, I think is correct. And then if you then say this is now relating to u minus iv, u is given by u cos alpha minus I, and then the v is u sine alpha. So they match up. So now if we look at the stagnation flow again, so here, what we have for our complex potential now is W is Z squared over 2 in this instance. So now, if we were to try and go back here and think about what U and V might be, our velocity components, do you have any idea or any intuition what they might be here?
Okay. I really want to just jump into calculating it, I guess. Yeah,
perhaps we could do it that way.
It's got to be something such that the zeros of the y component all live on the x-axis, and the zeros of the x component all live on the y-axis.
The axes are key, yeah.
Right.
Well, if you satisfy the axes, everything else should follow, really. So along the...
Like if it's a sufficiently natural-looking formula that satisfies that.
Yeah, pretty much.
I guess that already tells us that... Let's see, what's the convention? So we're calling u the x component?
Yes.
So the x component has to be something that's 0 when y is 0.
Yeah.
Right? So it's going to be y times something. Right? And then similarly, v is going to look like x times something.
Yep.
Right? And then I'm saying, what is my x component? In general, it's positive when x is positive, negative when x is negative. So that feels... But I don't want to just multiply by x, though, because it's not 0.
I think these may be the wrong way around.
Right, okay, yeah, so sorry, yeah, okay. Because the x component of all of this, when x is equal to 0,
yeah,
of course.
Yeah,
okay. X. And then the y component of this is going to be y times something. But in this context, it looks positive when y is negative, negative when y is positive. So maybe by -1. And then I'm comfortable with the x just looking like what it is. So
and this would even work with the 0 at the origin as well.
Yeah, and like if there isn't a need to add anything more to these
Let's
for it
just
to
leave
look
it
like
simple,
this picture, then it's like as good a guess as anything else.
Yeah, and it's perfect, because now if we do dw by dz, we of course just get z, which is x plus iy. And so since that is u minus iv, u must be x, which is what you've written down, and v must be minus y.
Okay.
And then for the line source, it's a bit trickier to see the line source, and it's sort of crying out for polar coordinates rather than x and y, but you can sort of hopefully take my word for it that what you're going to get is you get this 2 pi coming in from the angular dependence, and then it's log of z.
Sorry, this is a q?
This is just a constant.
A constant,
but
okay.
we label it as q. So it's an integration constant. We call it q because you think of q as like a volume flux or like a strength of a source.
Sure.
And this is actually going to relate to the strength of the source.
Okay, yeah. Like
So
Gauss's law, kind of.
Yeah, exactly. You can literally do the integral for the source strength and it comes out as q.
Okay.
With this function. So we've got this one for the source. We've got this one for the stagnation point. And then we had the exponential for the uniform flow. So now that we've got the potentials, kind of what you spotted when we go back to your lovely diagram earlier with adding of the vectors. And it is actually, it's complicated, but it is a lovely diagram.
It's up in the museum.
So what kind of is going on here, and you completely figure this out, is like you kind of just add your potentials to get the new potential and the new description of this velocity field.
And to be clear, the reason that's true is that the equations governing this are linear.
Exactly,
it's
yes.
Just divergence is 0, curl is 0, and those you can add together.
Yes,
okay.
Yes. And the big momentum Navier-Stokes gives you an equation, but that equation turns into Bernoulli's theorem.
Okay.
Which tells you something about the flows, but isn't used to solve for the velocity.
Okay.
The solving bit comes from the irrotational and the incompressibility, the divergence and the curl both being 0, nice and linear things. Put them together, you get Laplace's equation, again, super linear. So like basically you're solving Laplace to find these different potentials in these different situations. And so we get these three functions. And now what this means is that when we want to know, for example, the potential here, we literally just add the uniform flow, where now our angle will be 0, to the potential for the source, and that then gives the potential for this, and then once you've got the potential, that tells you the velocity field.
Okay.
So and it does match your intuition. You have this uniform flow out here, you have this envelope region, and then you have the flow coming in, and sort of inside this, you get this kind of behavior, and then out of here it's as though it doesn't exist.
Interesting. Okay.
That's what happens when you add the two together. Now the whole purpose of this is finally going to get onto this idea of method of images. So we've got like a basic idea of some flows, we've got something about these potentials, and we kind of just add them all together to get what's happening. So now you can say, well, these are all very, very idealized situations. So what if we start adding in boundaries?
Right.
And this is something that you mentioned a few times. You're like, I want boundary conditions. I want to know what's going on here. So let's suppose now we have a wall or a boundary. And then here we have a source.
Okay.
And now we want to know what's the flow field going on here.
Right. Okay. Because it's going to come somehow once it's at that wall, it needs to smooth itself out. Right.
Yeah, exactly.
And I imagine it's not that the wall has its own complex equation that we're going to bring in. Like, this is the complex equation for the flow potential when a wall is involved.
No, we can actually get the answer using everything that we've got so far.
Okay.
As a starting point, so if we take this to be the axis, and we say, right, so now we've got the wall is on our y-axis, and this is located at, let's say, x equals d.
Okay.
Then we know that the potential for that thing must be q over 2 pi. And instead of being log of z, it's going to be log of z minus d.
Sure. Okay. Yeah.
So we just shifted it a little bit. But then, of course, that only works without the wall.
Right. And the whole challenge is...
well, how do we modify this given we've got this wall and we want to know what's going on? Because exactly as you've drawn, this is going to come out, and the point is it's going to have to turn and sort of go up. And then these other bits are going to kind of do that. So there's perhaps past here, this bit doesn't know.
Right.
But in here, there's going to be some effect.
So, I mean, with the log, this is giving us a pole in our complex equation there.
Yeah.
So it's kind of like we want to continue having that pole, but we also want to somehow guarantee that the x component is 0 along this whole thing.
Yeah.
So a formula that has x component 0 but also has this as a pole. Which is not obvious to me.
No. The clue is in the name of the method.
The method of
images.
Okay.
So if we were to treat our wall as a mirror.
Okay. Yeah.
Then,
I like where this is going. Okay.
You literally take the wall as a mirror and reflect to
and
the
we
other
have
side.
another source sitting
So
at
if we had
negative
a
D.
source at minus D, and we had this source doing its thing, it would of course form the same kind of pattern over here.
So they like perfectly counteract each other.
Exactly. So it would perfectly, that's what the wall is kind of doing.
Right.
The wall being there would have the same effect as two sources
It's like
and colliding.
if you see yourself in a mirror and you give your mirror self a high five. It's like, yes, your hand stopped there, and you can't be sure that it's not actually just another copy of you. Because
Yeah.
all the physics that just happened is the same as
Absolutely.
if it was some... Okay.
Absolutely. So if this is the...
Oh, that's clever. So then we just add this
Exactly.
to log of z plus d.
Exactly. So this is then just q log of z plus d.
That's lovely.
And so that would then give us the potential
You take its complex
with
derivative,
the wall.
and that gives you
And that gives
velocities.
you, exactly.
And
then
it'll
you know
work
the
out
whole
such
thing.
that along the wall, the x component is 0. Oh, that's
Yeah.
lovely. That's
Yeah.
just really clever.
So that was our
Because that's way
first...
smaller than I would expect it to be.
Yeah,
As a solution,
yeah.
right?
It's still quite a mess. Don't,
I mean,
let's not pretend
yeah.
otherwise. But
Well,
yeah, because
sure,
you could,
but-
of course, combine these into using the rules of logs as well, if you really wanted, into
Oh,
a
right.
single logarithm.
Okay, yeah,
But,
okay, great. And then it's just, multiplying them, which is grand. But you would think because this is a lot of complexity.
no,
Right.
absolutely.
I mean, just the fact that you can describe any of them with this nice little potential equation is sort of neat.
Yeah. So then that was a sort of the standard example, and then you can also do the same with corners.
Okay.
So now this is a wall, and this is a wall, and I've got a source here. It's some complex number c. So, given your newfound knowledge and love of the method of images, Grant.
It is a newfound love. Yeah. I'm treating y-axis as a mirror.
Yep.
And I'm also treating the x-axis as a mirror.
Exactly.
So there's a reflection of itself down here, and then another one over here.
Yeah. You need all four to be able to cancel out in
that makes
both
sense.
directions all relevant components.
And then so what we'll have is going to look like q over 2 pi times, okay, I guess log of z minus d plus ei.
Oh, I was just going to
Something
call
like
it
that.
C, but yeah,
Oh,
if you
just-
just call
oh,
the
just
point
C.
C,
Yeah,
if you just
okay.
call the point it's at is
Well,
C.
because I want to be able to describe, I guess we can describe it with this complex conjugate.
Yeah,
Z
it
minus
should
C.
just about work with conjugates.
And we don't necessarily have to write it all out.
No, and then we're going to have that one will be at
Z minus,
C bar, yeah.
yeah,
And then
what is this whole thing is inside? Log of Z, okay, so what is that, negative? Yeah, this is negative C
negative
bar,
conjugate,
right?
yeah, exactly, yeah.
So Z plus C bar, and then log. I just, for completeness' sake.
I like how you
you.
started with, I'm not going to write this all out, and then you were like, I need to write this all out.
Yeah. Wait, so we've got minus C plus C bar minus C bar plus C.
Plus C, yeah.
Right, that's sitting there. Okay. Cool.
And so then again, it's just the four all add together, and that describes the flow field that you would get here.
Mm-hmm.
You're going to have this thing, and then apart from that, it's going to kind of do that kind of behavior. Sort of like that.
Nice.
And that's described by this
That's
trivial
lovely.
formula.
That's absolutely lovely.
Okay, and then the very, very final, so we can get really, really go to town with these, is to
Hexagonal
consider...
mirrors or something.
we absolutely could continue with the sort of polygons for sure, and then
Okay.
just positioning various ones.
But you've got something better.
I've got something even better, because I've got the infinite channel.
The infinite channel.
The infinite channel. So now we have walls on both sides,
Yeah.
and then we're going to have a source here in the middle, and we want to be able to describe mathematically what's happening here. So now our initial thought is, oh, method of images. That's it's our new favorite thing. So then you would say, right, well, I put one up here. So if this has width, if that's A, and this is also A, then what we need to do is we then need to go another...
A.
Yes, so this is going to be at 0, the real axis. So there's going to be another A, so this will now be at 2, IA, and then 4, IA. So I've kind of given away that we need to keep doing more.
Well, because if you're in a room with a mirror in front of you and a mirror behind you, it's not like you
Exactly.
see just one reflection of yourself.
You've got to keep
You see
going,
this,
yeah.
like,
There's one on
infinite
each side.
array of-
So you've
of
got to keep
reflections of
going with
yourself.
these every 2A
Yeah.
all the way, and you create an infinite line.
Great. And so now we're
of
going to have an
sources.
infinite series.
And now we've got an infinite series.
Great.
If we think about where these are, you could describe this position as 2nia as you sum over n.
Over all integers.
Over all integers. Yeah. And so to put down the full potential, you'll get W is Q over 2 pi, the limit as n tends to infinity of the sum of log z minus 2 nai. So this would be the true way of writing this down.
And you've done it properly, like where you're only going to get convergence if you let there be cancellation between the positive and the negative, I imagine.
Quite well, that's the point. We don't know if this converges at this point.
Oh, okay.
We have absolutely no clue whether this is a sensible thing, whether this is complete nonsense, like what on earth's going on. Other than physically using our method, this seems to be the way to approach the problem. Is to just keep reflecting, and everything should cancel out, and give us the potential for this source.
Well, the thing is, as we take the derivative of this, it looks like a harmonic series.
You know what you're doing. That's exactly what we want to do, because we know that u minus iv is dw by dz. So we can take the derivative, q over 2 pi, and then take the limit, and you get 1 over z plus 2z times the sum of 1 over z squared plus n squared times 4a squared. Where this is now going from 0 to infinity. So I sort of skipped over a couple of steps. So it was differentiate it, then rationalize the denominator, make it look nice, and then I can say, oh, but this is a 1 over n squared sum. I know this is going to converge, I hope, and then I can take the limit, because I now know that it exists. And then you compare this to a known sum. So the known sum here, I say known, it's potentially not that well known, but there's certainly a sum which is the sum of 1 over n squared plus
Will this be cotangent?
b squared. Yes, it is indeed. Is equal to minus 1 over 2 b squared plus pi. It's a coth, so hyperbolic cotangent of b pi over 2b. So we have this sum, and then this looks like this with the appropriate choice of b. And so you rearrange all of this, so we know that dw by dz, which is u minus iv, which is q over 4a, cotangent hyperbolic pi z over 2a, as your final velocity field.
Lovely.
And now we can then integrate this back up and get what w should be in the first place. So it turns out the sum was convergent after all. And get the log of a shine function.
Nice.
As our original potential field.
Yeah, but I mean, if we have this is the real.
Yes, so this is the one that actually allows you to then draw the picture. So if you were sort of trying to go back and think what these things look like, you can plot these for different values, and you just take the real part of this, would give you the x component of the velocity, the imaginary part gives you v, and you sort of get what you would hopefully expect, which is sort of these things are doing this. So this kind of looks like the hyperbolic cotangent, and then these ones sort of just come out and kind of like that.
Lovely. Oh, that's so clever. That's so clever.
So
to have like that infinite reflection,
yes.
And then it all. Yeah.
I thought, well, when you said you wanted to learn fluids, I was like, I've got to think of something visual, like you know.
It didn't have to be.
Well, I felt like it did. So the method of images, one of my favorite things in fluids. It's obviously quite advanced, some of the the maths that's involved, but hopefully the actual technique itself.
For someone to be very like satisfied with it, you'd want to be comfortable interpreting the derivative of complex, like when you think what's the derivative of log z, like having some image in your head for what that means.
Yes.
And like if you have thought about it a bit, the idea of that sort of being the same thing as curl-free and divergence-free, like it jives.
Yeah.
If you haven't, it's like it'll come there at some point. But if someone's willing to take for granted the idea that these are accurate descriptions.
Yes, of course. So I've sort of magically plucked these potentials out of the air, but then once you sort of, as you say, once you take that and say, okay, these are the potentials for these situations, then you can work with them and create these neat.
But the core almost doesn't even run. The core cleverness is that, hey, these are linear, so if we can just add them on top of each other,
absolutely.
our channel situation would behave exactly the same as if there was an infinite array of sources providing the exact cancellation. Like that doesn't that key idea doesn't rely on complex analysis, but
That's
it's
true.
just completely beautiful.
Yeah.
I love that. I love that.
Good. Well, I'm very glad. Thank you so
Thanks
much.
for showing me.
You're very, very welcome.
Very wonderful.
And thank you everybody for watching. If you haven't already, I'm sure you have, check out Grant's amazing channel, 3 Blue 1 Brown. And if you've enjoyed this video, please do subscribe to my channel, and I will see you soon.
Awesome.